You see, this is a new development which I want to fit into the scheme which I've been trying to plug for a long time. Now, that's not the first slide. How did that happen? Oh, yes, no, we've got the wrong end. Yes, excuse us.
No problem.
That's it. Yes. Now, let me start with the observation which really convinced people of Einstein's theory of general relativity, and it was to do with the bending of light by the sun. And this shows you the effect. You see, suppose we have a star pattern, and you can see the inner little ring of stars. Hello. Yes, perhaps I should start again, should I?
But, it's in progress, so you can carry on.
Yes. So we see the image of the sun and the background stars. And let's suppose that if the sun were not there, the stars would form that little circular image up and to the right, the inner one. And there might be, say, a circular pattern of stars or something like that. And the presence of the sun pushes the image outwards, because you see the light gets bent round the sun. And so that means you're seeing things a little closer in towards the center of the sun than you might have thought. In other words, the image gets pushed outwards. And so the image gets pushed outwards. And if you found a little circular pattern in the sky, which is imaginary pattern of stars, then as it gets pushed outwards, of course, the pushing outwards gets less and less the further out you go, whereas the angular diameter, the angular from the center of the sun, the angle it makes will be the same. So that means that the image of a circle will get turned into an ellipse. So this is the effect of the curvature of space-time will distort the image of a circle into an ellipse. Now I want to show in space-time terms the sort of thing that looks like. So I'm imagining, say, an observer up at the top looking backwards along the light cone of the observer. The light rays, I'll tend to draw them at 45 degrees as though the speed of light, well, you see, if you're using meters for your distance, then you have to have light meters for your time. And so the idea is that the speed of light looks as though it's tilted at right angles to the vertical in your picture. So you're sitting at the top, the rays coming into your eye form this past light cone. And as this light cone goes through the curvature, it gets distorted. And the effect of the curvature of empty space is what's called the Weyl curvature. You see, the full curvature has 20 components. 10 of them correspond to the Weyl curvature, which is the conformal curvature. And that is directly measured by the bending of the light rays, or if you like, the converting of this circular image into an elliptical image. So you see it squashes it sort of flat, somewhat flat. It's only a very small effect, but this you see in this picture the general action of the effect. If it was the Ricci tensor, you see the full curvature is split into two parts. The 20 components goes into 10 components of the Weyl and 10 components of Ricci, which is what's left. And the Ricci tensor, part of it is to do with the trace and the cosmological constant, and we'll talk maybe a bit about that later on. But the main point is that the part of the Ricci tensor which affects the light rays is the trace-free part, and that just focuses inwards. It doesn't affect the distortion. So the things which measures the gravitational field, that's the free gravitational field, which is measured by the Weyl curvature, is this distortion effect. Now let's move on. I now want to talk about cosmology. And this is a sort of rough picture of the history of the universe, starting from the Big Bang. Then it expands rapidly, slows down a bit, and then it starts to accelerate in its expansion. Well, people call it the mysterious dark energy. I always thought of it as the cosmological constant. It's what Einstein introduced in the early days of the subject, and then retracted and then introduced it again. And he got it for the wrong reason, but it was probably true that it's right there. And I remember going to conferences and people will, at the end of the conference, say, well, maybe the end of this conference we'll know whether there's a cosmological constant or not, and what its sign was. And then people discovered this, and they thought, this is the mysterious dark energy that nobody had ever expected before. Ridiculous. It was one of the terms of Einstein's equation. Of course, it may be something else, but the cosmological constant term does lead to this accelerated expansion. So as far as I'm concerned, it's just the cosmological constant. Now, I've drawn the picture as though the universe was spatially closed as you go around. If you look at the back, it's not really. It could be going and wiggling and all sorts of things. It's just for the purposes of the diagram. It's useful to sort of pretend it's closed when it's almost certainly not. It probably keeps on going and going, as I was trying to indicate with the wiggly part right at the back and the top. Okay, well, that's my cartoon of the universe. Now, let's imagine a collapse. Suppose the universe were to collapse in exactly the reverse of this picture, then you would get the reverse of the Big Bang at the top. I've just turned my slide upside down. That's all I've done here. And the so-called, well, the Big Bang is now a big crunch instead. So that would be that picture. However, that's a very unrealistic picture because irregularities will cause a much more complicated business. It's like lots of black holes, and the singularities in black holes are completely different from the one in the Big Bang. You have the Weyl curvature absolutely dominating what goes on. And there was a work done by Belinsky, Lifshitz, and Khalatnikov, which seemed to indicate in the generic situation, you would get very, very wild behavior with Weyl curvature completely blowing up and going wild and crazy. So this is the sort of thing you would expect for a general collapsing universe with irregularities. There could be black holes, and that's meant to be indicated by the black lines going up, but they needn't be. But when the universe sort of collapses inwards and inwards and inwards, you would get much more black holes forming, and you would get this great mess. So that's what you would get for the remote future. But if you turn that round the other way, for a general Big Bang, you get nothing like what we see. You have this crazy business going on, Weyl curvature all over the place, and it's nothing like what we actually see. What we actually see is more like the picture I showed you a minute ago. In fact, now I want to indicate another feature that people tend to talk about in their discussion of cosmology for various reasons, which I won't go into. They tend to think that in the very, very early stages of the Big Bang, you have this thing, which I put my magnifying glass on it to have a good look at it. And this apparently looks like another Big Bang. So you've got the Big Bang, very uniform, stretched out, and this is what's called the inflationary phase. And that's introduced for all sorts of reasons, which I never believed. It seems to me that it doesn't solve the real problem, because the real problem is why the Big Bang was not like the time reverse of this great mess we saw as what a collapsing universe would look like. You have to bear in mind that this inflationary stage, which is really meant to be just an exponential expansion of the universe, pretty well uniform all the way around. Bear in mind this picture, because I'll come back to this later on, but for the moment, I just want to say that is the conventional picture of cosmology, that there was this phase right at the beginning, which I always had a lot of trouble believing in. It didn't solve any of the problems that I thought needed to be solved, the prime one being why the universe was so smooth in the Big Bang in the early stages. Now, this is a very early picture of the microwave background. You see that here we have the background radiation that was discovered, and this was what really convinced people that the steady state model, for example, was not correct, that there really was an early stage of the universe which was very, very hot and dense. And if you assume that it was some kind of equilibrium, then you would get the frequencies. The frequency is along the bottom line, and the intensity is upwards. And this is the curve, the Planck curve, which is what you get if you have a very absolutely random situation. It's a Planck curve, That's what it means. You're looking at total maximum entropy situation. And what we see is this curve with the error bars. You will see those are the lines going up and down, the error bars, but they are exaggerated by a factor of 500. So if you really put the actual error bars in, there will be less than the thickness that they incline, an extremely perfect Planck curve. The point I'm making here is that as far as the matter that you're seeing, the dominant matter in the universe, it looks as though it's absolutely at maximum entropy, very, very closely like that. Now, that is a great puzzle, you might say, and I want to explain how I'd resolve this puzzle. What is the puzzle, you see? It looks as though the universe started off with the matter being at absolute maximum entropy. Maximum? Isn't that universe supposed to be expanding? And isn't the universe supposed to be, well, if you've got maximum entropy to begin with, where's it going? I mean, it can't get any bigger than the maximum. So how could it be consistent with the second law of thermodynamics? Second law of thermodynamics says that the entropy goes up and up and up, which means it gets more and more random as time goes on. Entropy is a measure of randomness. And so why is it not simply maximum entropy already? So how can you get any more entropy? It's already at a maximum. So here is the resolution of that puzzle. For some reason, people have a lot of trouble with this. I'm imagining in the top three boxes, this is just a cartoon of a gas in a box or something like that. And I imagine it's tucked up in one corner. Imagine you have a smaller box, and all the gas is tucked up in that corner. You open the box, it spreads out. As entropy increases, uniformity increases. Well, that's what happens with most things. That's the sort of general expectation. But how about gravity? With gravity, it goes the other way. I'm imagining here, the bottom three boxes, because you go to the right, suppose we had a random display of stars just spattered around randomly, then they will start to clump. And as they clump, the entropy goes up and the clumpiness goes up. It goes the other way around and you get black holes. That's where it really, really clumps and the entropy goes absolutely shooting up enormously with a black hole. So it's still consistent. Both pictures are consistent with the second law of thermodynamics, but when it's gravity that dominates, the picture looks very different. Uniformity is now very low entropy. The clumpiness, particularly with black holes, where the entropy goes absolutely shooting up to an enormous figure. So that what we see is top right and bottom left. We see uniformity, and that means that as far as the matter is concerned, yes, the entropy is pretty well at its maximum, but what about gravity? Gravity is pretty well at its minimum. So that is the puzzle. And it seemed to me people never quite appreciated this huge puzzle, which to me was an enormous puzzle of the universe. Why was it that the gravitational degrees of freedom were very, very constrained? Nothing else seems to have been constrained in that way. Here I also have a picture, it's sort of a side issue, but it's really due to Schrodinger. And he was making the point that you see, what do you get from the sun? Well, people say, oh, you get energy from the sun. He says, oh, no, you don't. Because in the daytime, sure, you get the energy, and the photons come in from the sun. And the night, they go all the way back again, pretty well. Go back. Well, actually, a little bit more goes back because of global warming. No, sorry, fewer go back because of global warming. But I'm afraid the major effect is just as much goes out as come in. So it's not energy that we get from the sun. What we get from the sun is energy in a low entropy form. That is to say, hot photons, and when they go back as cold photons, infrared photons, that means you need many more photons to take the same amount of energy away. That is many more degrees of freedom, much more entropy. So that's the situation. And I really just want to emphasize that the sun is there. Of course, there are all sorts of other reasons, nuclear forces and all sorts of stuff going on. But the main point is it's there at all. And it's there because of gravity. And gravity is clumped. And that is what we're living off, if you like, the low entropy in the gravitational field. And that's the point of this slide, really, is to show we get that life on Earth and everything, all the interesting things that's going on the Earth come from the fact that the sun is there at all. And it's there because Okay, it's hot for all sorts of reasons, but the main reason it's there, and it's there because it's clumped and had the opportunity clumped from previously uniform universe. So what we seem to see is in the Big Bang singularity, this very peculiar situation of the gravitational field not being thermalized. I mean, you've got the gravitational degrees of freedom sitting there waiting to be used, whereas in the remote future, the Barrow curvature. I can't quite read what I say on my slide here. Let me move on. I don't think I need that slide. That shouldn't have been here. Sorry. That's to do with the principle of equivalence. I don't quite know. Oh, yes. It was meant not to be there. What's happened? Oh, I see. We've jumped to the end for some reason. That's not, what's the next one? Ah, that's it. Thank you. Yes. Now, this is the picture of the universe on the left that we seem to have a very uniform Big Bang and a very irregular remote future. Well, that's not quite the picture. You get black holes and all that, but the dominant thing in the future is things like photons. The simple, I just go over to the simplest picture, just say it's photons. It's not really as easy as that because you've got all sorts of other things. We still have electrons and positrons running around. And there may be a case for saying they gradually lose their mass, which I've tried to argue for reasons which I don't want to go into here. But the point is that the remote future looks as though it sort of gets very, very rarefied and very uniform. The Big Bang is such that, see, how do you characterize the fact that the gravitational degrees are not activated? Well, the Weyl curvature is very small, maybe zero, but the characterization, which was really initially introduced by my former student and colleague Paul Todd, who suggested here's a much better way of doing it. I'd sort of thought of it before, but he really worked it out properly, thought of it independently, and I give him full credit. He said, well, the best way of talking about what's special about the Big Bang is to say if you stretch it out conformally, and I'll say a little bit more about what that means, stretch it out conformally, it's nice and smooth and makes a nice boundary. And I'm now saying, in addition to that, if you take the remote future and squash it down, apart from odd points, which are the places where you have galaxies and the galaxies make black holes, and the black holes come in earlier, who knows when, and then they start to run into each other, and you end up with one enormous black hole in a galaxy, and then the galaxies in a cluster remain more or less bound as the universe expands, and these clusters then the galaxies in the cluster will run into each other from time to time, and their black holes, their dominant black holes will run into each other eventually. It takes a while before that happens, but eventually the black hole will be pretty well dominate the whole thing, swallow most of the stars. Some might escape, it's quite possible. Some material might escape, but probably the majority of the material will eventually be swallowed up by the black holes. These black holes will form odd spots in the sky, but they will be little anomalies, if you like, in the more or less uniform universe in which the universe gets very, very smooth and rarefied all the way around. So the picture I'm drawing here, I'm forgetting about those, the black holes, if you like, and the little points on the remote future. I can squash it down and form a conformal infinity, which, because the cosmological constant is positive, it has a space-like character. So I've drawn it horizontally in the picture. It's a space-like boundary at the future, which is squashing down the future infinity. And now I'm stretching out and using Paul Todd's criterion, that I say stretch it out, and the criterion is that it's smooth when stretched out. And when it's stretched out, it looks awfully like the remote future. You might say, what could be more different? The remote future is very rarefied and very, very, very cold. And what's the Big Bang? It's very dense and very hot. What could be more different? Well, they could be a lot more different. In fact, they're not all that great different. But if you stretch out one conformally, and I hope I've got that in my picture here, if you wonder what conformal means, the person to go to is Escher. This is a nice picture by M.C. Escher, the Dutch artist. And he liked, when he learnt about hyperbolic geometry, he had a real go at it and had, I think, 5 pictures of his. And this is actually the first one, but in some ways I like it the best because it has these fish-like creatures which have circular eyes. And the point is that the closer you get to the boundary, they still remain, the eyes remain circular. So the conformal feature of it means that if you squash in one direction, it squashes just the same amount in the opposite direction, and it preserves small shapes. And small circles remain as circles, as you see in this picture, but the density of them gets bigger and bigger as you get to the edge, but you have infinity represented. So the conformal infinity in this picture, this is not Euclidean geometry, this is hyperbolic geometry. It may be relevant to the universe as a whole, but that's not the point I'm making. From space-time point of view, you do have a boundary of this nature. Whether or not the space is closed or open doesn't make that much difference to the picture. Now, here I have a picture of the light cone. The metric has 10 components. The 9 independent ratios of those 10 components give you what the speed of light looks like. And so it's a space-time picture, if you like, with the speed of light represented at right angles to the vertical. And so you see the light cone drawn sort of that way. You don't have to draw it that way, but just to get the general picture. The speed of light is represented by this sort of orange cone. That's where a light ray would be tilted over it that way. And actually massive particles would have to be within that cone. That goes less than the speed of light. But at the bottom, I've written the 2 most famous formulae of 20th century physics. Of course, there's E equals mc squared and E equals mc squared, that tells you that energy and mass are equivalent, C being just a constant. But earlier than that was Max Planck's formula, E equals h nu. Nu, or F, sometimes people write it, is a frequency. H is just a constant. So energy and frequency are equivalent. Einstein says energy and mass are equivalent. Max Planck says energy and frequency are equivalent. Put the 2 together, it says mass and frequency are equivalent. In other words, where you get frequency, and I've tried to indicate that in my picture, it's not just the cones, but I'm putting these sort of little hyperbole in, which are the surfaces of each equal time. So the particles, when they're supposed to imagine they're clocks, and as the first tick and the second tick and the third tick will be represented by those little hyperboloid surfaces in the past cone and in the future cone, and how closely they're packed is one number. The 9 remaining numbers tell you where the light cone is. So conformal means we know the light cone, but we don't know how packed it is to give you the mass. Now, if you don't have any mass, which is what I'm claiming is that more or less the situation in the remote future is pretty well photons. The story is more complicated really in the remote future, but let's take the simple picture. So it's just photons. Photons don't have any mass, so they don't know big from small. They just know the light cone. What happens at the Big Bang? It's actually, the story is rather easier there because it's so hot and so dense, well, mainly so hot. That means that the particles are moving around at such an enormous speed that their mass is almost entirely due to their motion. The mass of the particles is more or less irrelevant. It's completely dominated by the energy of their motion. So everything is in effect massless. So at the Big Bang, you have in effect massless, and the remote future, in effect massless. So the idea is that those 2 ends, you don't know big from small, and so they're not so different as you might think. And you can think of it, it's just a light cone, you see, I'm trying to say, rather than having all this structure here, which gives you a scaling, and that's 9 out of 10 components, calling the ratio of the 10 as 1 component. And this is where you've just got the 9, which determine the light cone. It's most of the geometry, but it's the most which I'm mostly interested in. And I'm trying to say that if I stretch out the Big Bang and I squash down infinity, I get something pretty similar. You might say the remote future is pretty cold and pretty rarefied, and the Big Bang is very hot and very dense. What could be more different? Not at all. If you stretch out the Big Bang, it gets colder and less dense. If you squash down infinity, it gets hotter and more dense. So they're actually not very different. That's a surprising thing which you have to get used to. The squashed down remote future is really very, very like the stretched out Big Bang. And I'm going further than that and saying not only are they very like, for some reason that picture keeps coming back on me. I don't want it. What's happened? Why is the picture doing that for me? It's a good picture for other reasons, but it's not what I want for this talk. Yes, now that's it. Yes, now we're getting there. It seems to jump for me. Yes, that's it. Yes, yes. Or can I go back one? Yes.
Yes. Yeah.
Maybe I pressed the wrong button, did I? No, I don't think I did.
Okay.
I did. Okay. Yes, so that's the picture I was just talking to. And now here is the crazy idea that our aeon, as I'm calling it, from its Big Bang to remote future, because the Big Bang looks very much like a remote future, and the remote future really looks very like a Big Bang, because we haven't any mass at the join. When mass is gone, they do look very different. You don't have anything to scale. And so what I'm saying is not only do they look very similar, our Big Bang was the continuation of the remote future of a previous cosmic eon. So that is the picture which I'm presenting. And let's see if I get it right here. One thing I also want to make is that certain things can get through. The things that can get through are photons, for example. You could imagine that, but then they have a trouble on the other side because it's so dense and hot, and photons don't get very far. They start to scatter all over the place. The best thing to get through are gravitational waves. Gravitational waves go sailing through. They don't care about the dense matter at the other side. Gravitational radiation goes clean through from one side to the other. So that's the argument I'm making. And there were various attempts to persuade people about CCC. And one of the arguments had to do with this. I was imagining collisions between, you see that the horizontal plane is the crossover surface, which I put another dimension in there to make it look more like a three-dimensional surface. I put it looking like a plane, but you have to imagine there's another dimension. And I'm having two events, which say black hole collisions. You might have huge black holes running into each other. They would produce a huge energy lost in the form of gravitational waves, and these gravitational waves will hit the crossover and come through onto the other side. And you might see their effect in one way or another. And various people, originally Vahe Gursajan was looking at this in one way, and then my colleagues Christoph Meisner and Pavel Nurowski and people looked at it in a different way. And they came to the conclusion that there was some evidence of a signal. This picture is due to Vahe. That's what we were looking at were circular rings, of which the centers are plotted here. These circular rings would be the result of supermassive black holes running into each other, producing a gravitational wave signal. And he thought to get a sufficient enough signal, he was looking at the variance in the temperature might be anomalously low, and not very much anomalously low. So he looked for at least three rings which are concentric. And if you find three rings which are concentric, you might get a significant figure. And the claim was that they clump in this extraordinary way. The red, I think, is colder and the blue is hotter, I think. Never mind about that. But it's curiously non-uniform in the sky. I've never had an explanation of this picture before. It does seem to be a good picture, and it's just sitting there in the literature without people paying much attention to it. Now let me move on without ruining the picture. The other effect I would talk about is the Hawking evaporation of a black hole. The huge black holes, which I was talking about before, if you wait for a long time, and you've got forever to wait, so it is a long time, say in terms of 100 years, it's that sort of scale of time, they will gradually evaporate away, and they will cause little spots, heated spots. And this is the picture from the paper I had with Christoph Meisner and colleagues, where we looked for this effect. And this was the temperature. You imagine the crossover surface is right at the bottom. The decoupling or last scattering surface is the next horizontal line. And that's where you start to see something. And it would cause a sort of heating, spot of heating. And we do see these spots. We see these spots with a confidence level of 99.98% confidence level. There is a certain anomaly about these, which they seem to be too big by a factor of 2. And that is something which requires a subtle explanation, which I won't try to go into at the moment. It's a problem which is not totally solved at the moment, but I think we do know the answer to this. But we do see these spots in the sky with that confidence level. And why do people ignore that? I don't know, they do. Now, I want to move on to the main subject of this talk, which is a new effect. This is the effect discovered by Alexia Lopez, and the rings indicated here, where the ring in the middle is the big ring, I forget what it's called, the large ring, and it seems to be a circular pattern of galaxies. And what are they doing as a circular pattern of galaxies? And then the big one is the arc, which she told me is very likely also a ring. It looks as though it's a ring which is not quite centered at the same place as the other ring, but they're not so far away. So I'm trying to imagine that these rings are the result of gravitational waves coming from a collision between galactic clusters or supermassive black holes in galactic clusters, and big clusters. They would have to be very big clusters. And so you get enormous black holes, and these black holes take a little while to find each other. And then when they run into each other, wham, there's huge, absolutely huge, walloping signal of gravitational waves which come through from one eon to the next. And they should do, according to the theory, they should certainly come through. And what do you see? Well, maybe you see this. Now, the real main picture I want to show is the last one here. This last picture is a conformal diagram. You notice these sort of horizontal lines. They're meant to be sort of bluish at the bottom and reddish at the top, because that is the remote future of our previous eon, and then comes across to our Big Bang. And then as you up the picture, you find our remote future, and that will be the Big Bang of the next eon. So our Big Bang came from the remote future of a previous eon. When the universe forgot about mass became effectively 0. And so that means that it's physically sensible to join the pictures together. Now, what I'm imagining here, I hope you could see it in the picture. There's some arrows which I really want to get rid of. They should be not there. Can I get rid of the arrow? Doesn't move. Oh, that's moved. Fine, yes. I can bring it back again, I suppose, now. Okay, so I'm supposing, you see, these rings that Alexia finds are so big that if you trace back, suppose they were an explosive event of some kind which produced the rings. Well, as you trace them back in the conformal picture of mine, they go before the crossover. If you take the conventional picture, then you would have to have a slab of inflation in between. Inflation ruins the picture. It's just a slab which you put in the middle, which can be any size you like, because inflation doesn't have much to say about that. The trouble is that if it's in inflation, you have to have a huge explosion taking place in the middle of an explosion, in the middle of inflation, and that doesn't make any sense at all, as far as I can see. But maybe they will come up with some crazy idea which will show how Alexia's rings can be initiated within the inflationary phase. But if you don't have inflation, which I don't have, I have the previous eon. There are things which inflation are introduced to try and explain. I believe they are all explained with having see, one thing is the Big Bang is a space-like surface. So if it was just an event which just came into being all at once, you wouldn't expect to have correlations between different points on that space-like surface. But you do find correlations. And that's one reason that people introduce inflation, as I understand it. Now, I don't need that because the correlations will come about because of the existence of the previous eon. Now, most strikingly, and in this picture, I hope you can see right near the bottom, two black points. Let's take the lower one. This would produce, in this picture, the great arc, because it's the bigger one. It makes the light cone of that hits the crossover surface in quite a big ring region already. It ought to be a ring in this picture. Maybe you can't see the whole ring for some reason, or maybe it is a ring, because Alexia was telling me that she thinks it could well be that it is actually a ring. So I was supposing that that's a ring, and that ring would be not sort of a puzzle in this picture, because it just says it's in the previous eon, as you might well expect, because that's where you have these huge supermassive black holes running into each other and producing these vast explosions. The ring would be the smaller one about here. They're not quite above each other in the picture. See, straight up and down would mean stopped in the picture. That means what we mean by stationary in the cosmology. That's straight up and down. So I'm saying that they're almost straight up and down. There's a little bit of a proper motion, and it would be interesting to see how much that is. And is it plausible? It's a good deal less than the speed of light, so that's clear. But if there was a certain amount of proper motion between the first collision in this galactic cluster and then the second collision in the galactic cluster, we come along maybe with a little bit of a motion from the first one, and that would mean that they're not quite concentric as you see them. So it's certainly quite possible, but maybe close to being concentric because it came perhaps from the same galactic cluster, which seems to me a plausible idea. Well, I'm just saying that's the picture I have, and maybe that does explain the ring. I should explain the picture here, as Alexia was making clear to me, that the points that you see here are far, far too big. They're not nearly the size that you see in this picture. That's an artist's impression. The artist's impression is telling you where they are. The points are where you see them, but the size of the spots is nothing like what you would actually see. The little pinpricks. Those little pinpricks would be the points that would be represent the black hole. Well, you see, I should explain. What one is supposed to be seeing, according to the picture I have here, is that the black hole collision comes through, the collision makes a gravitational wave signal. That gravitational wave signal comes through, goes straight through the crossover, pays pretty well no attention to the crossover, goes right through the other side until it starts to disturb the matter in the last scattering or decoupling surface. And there is where it creates enough disturbance to trigger off the condensation of a galaxy. So I take it that's a little bit of a puzzle where the triggering of the condensation to produce galaxies comes from. And the idea here is that it comes, maybe sometimes, maybe not always, but at least one of the ways it could trigger that would be this enormous gravitational wave signal, really a strong signal that comes through and triggers the amount of disturbance to cause a galaxy to perform. And as this thing is more or less a thin cone as it comes out, that thin cone means that it's almost what you see from us would be a circle, pretty well closely a circle. And that means that you will get the circular patterns that she seems to see. So it would be a beautiful example of maybe an indication of something which is of a different character from we looked for before, and maybe something which I hope might convince people of the plausibility of the picture which I'm giving you here. I don't know of any other explanation of why the gravitational degrees of freedom should be wiped out at the Big Bang. And there's no, inflation certainly doesn't do it. There's no reason whatsoever that I can see of any conventional model. However, this model does give you a reason because it is simply the remote future, which has been had zillions and zillions of years to stretch out, 10 to the 100 years or so, you would imagine, for the black holes finally to evaporate away and form the little Hawking points that I had on the other picture. And basically, they would form just very localized regions in the sky. Well, thank you very much.
Before I hand over to Alexia, may I ask for a few clarifications? The first is that the picture that you have so far given is entirely classical. Entirely classical.
Oh, classical.
Yeah.
Oh, I see what you mean. So you're worried about quantum mechanics. Well, you see, quantum mechanics may well have a role to play in the details of the crossover, but it doesn't seem to have much role to play in the overall picture. The crossover needs more explaining. I did a long time ago, I wrote a book about it, in fact, which was called, I've even forgot the name of it now. It was all about my ideas at the time. When people ask me, should they read this book, which I wrote, and I say, read the book, but don't read any of the appendices. They're all wrong. I don't mean that they're wrong mathematically. The mathematics is probably quite fine, but they're not the real explanation of the crossover. The crossover needs a different explanation, which may involve some quantum features. I'm not sure how important the quantum mechanical features are at that stage. But certainly you have to have a balance where the gravitational waves are dominant. You see, you have a different, I have a paper with Christoph, which is now on the archive, where we describe the overall picture we have. It requires a lot more working out the details. But the overall picture is that there is an epoch, as we call it, which is more or less contains the crossover. And in that epoch, the dominant physics, apart from the black holes, which will be little points in the crossover, which are just sitting out of the way, they're not the major thing. But the major thing will be the gravitational waves, which will be the dominant content of the universe. And when the gravitational waves are the dominant content, they allow for a conformal degree of freedom which is not present elsewhere. There's a new kind of conformal invariance which comes in at that level and allows you to go across from one side to the other. I don't know how quantum it is. It may be quantum to some degree, but the description that we have at the moment is a fairly classical picture.
I mean, that would not enable you to address the issue of the matter-antimatter asymmetry.
Oh, well, there were lots of, oh, sure, you'll have lots of antimatter and matter, but you see, the argument is that really the dominant thing is not the matter in the ordinary sense. The matter will, in fact, lose its mass, in effect, and will become, in effect, massless. And so you have effectively massless matter, which is that it's there, and it's not the dominant thing. You also have dark matter, which is much more dominant. And so you have to understand how the dark matter and the gravitational degrees of freedom fit in together and form a picture which is pretty coherent. And that allows for a conformal description of what goes crossover. That requires more work. I'm not prepared to talk about it at the moment because it's not a complete picture as now. But it does seem a plausible picture, and that the gravitational wave domination is what you have, which allows you from get one side. You see, there's no scale involved in the gravitational waves. It's a massless field. There's no mass there, nothing to give you a scale. The dark matter would do, and that's a complicated picture. It gets mixed up with the cosmological constant in a way which needs more exploration.
Thank you. And now I turn to the panelist, Alexia Lopez, Dr. Alexia Lopez.
Yes.
Could you speak about your contribution, and also about the other major large structures like Quiku?
Yeah, so hi, and thank you for inviting me onto this panel, by the way. Fascinating talk, Sir Roger. I did just want to ask some questions when I think about
Yes.
how the conformal cyclic cosmology relates to observational large-scale structure. So my first question is just a quick clarification. When you talk about rings, are these specifically rings that would be in our line of sight? Or would you see them at different angles if it was a structure? Would it be a sphere? Or are we specifically seeing just
Yes, let
one?
me explain a little bit more. I'm sorry, I was probably a little racing at the end. No, what you get are spheres, as you were saying. You have to think of how many dimensions is really involved. And the crossover surface is really a three surface. And the last scattering or decoupling surface is a three surface. So you have to think of a three-dimensional surface. And the explosions or the collisions between the supermassive black hole or whatever it is will be spheres. So basically they're spheres. Now our past cone hits those spheres in what looks like a ring to us. So why they look like circular rings is because they're the intersection of a sphere with our past cone. And it's really, if you like, where that sphere is, the sphere lies basically in I mean, it probably isn't exactly in exactly a surface. It's probably spread out a bit. But imagine it is a surface, a three surface, and so that sphere is sitting in the three surface. Our past light cone, as we look back, will hit that three surface in another sphere. Where those two spheres intersect is the ring that we see. So that the spheres will look to us like rings, circular rings.
So this would be, so for example, if this was triggering how the matter was forming, or like how the large scale structure was forming, would the structures themselves also be in ring shapes, or would they, is it the question is it just an observational effect, or is it also how it affects that structure formation?
I think what I should really say is it takes a little while. Certainly galaxies take a little while to form. So it's not really a sphere, it's a thick sphere. So you have a sphere, and the initial impulse is this outside. And then as you move in a little bit, you have in the picture, I'm imagining it happens quite fast in the picture, relatively speaking. And that is where the condensation is triggered in the initial surface. So the initial surface is the last scattering or decoupling. I'm never quite sure. They're not quite in the same place, I get it, but almost the same place. But to me, they're the same place. You've got this free surface, which is basically the last scattering or decoupling or something, and the gravitational wave signal hits it in a sphere. Now that sphere is thickened out because you've got things going on. They take a little time to condense. So it is to form a galaxy will take a little while. And so it's a little bit thick. It's not really a flat free surface. It's a slab. And as we look through this slab, you will see the time goes back in time as you go back. But so you're looking at a little bit of history as you go through there. But I'm imagining that is pretty quick compared with the conformal time as it has to take to get up to us. So it's a fairly rapid conformal time.
So, okay, thank you. But okay, so if you were to say what you might predict, then, I guess one of my questions would be, one, how many rings might you expect to see, and two, is there any kind of redshift you know, like a peak redshift where you might see these, or would you say that they could be quite thick in redshift, or would you say their signals would be expected to be, sorry, this is a lot of questions. Would you expect their signals to be quite strong, like the density contrast within that large scale structure of a ring? Or are we expecting to find maybe, you know, low density contrast across a large redshift interval? Or do you know how I mean?
I think this, let me try and answer the question as best I can. The slab is really not a free surface, it's got thickness in the first place. Now, also think of it as a three-dimensional surface. So the rings, if I'm just talking space-timely, not as what we see, in space-time terms, the rings are spheres. So each of these gravitational wave, bang, comes together, through from the previous eon, produces this impact onto the last scattering surface and produces a sphere, because the surface is really a three-dimensional space. So it's a sphere. That sphere has a certain thickness because the outside of the sphere will be the gravitational wave itself, because that will be pretty much an impulse, I guess. And then it takes a little while for the physics of that, what it does to the last scattering surface may take a while. And it will no doubt provide what looks to us, yes, how do I say this? It's the intersection of two spheres, really. That's why it's a ring. Because you've got the sphere, which is the gravitational wave impulse, and you've got the sphere, which is where our past light cone hits the last scattering surface. They're both spheres. Now, how they intersect, there's a difference. They could be almost touching, they could be almost orthogonal, they could be almost touching the other way around. So you have a lots of scope for different temperatures, put it like that. So they could be hot if they're just almost touching, middling, or cold, I guess, if it's the backside, because that's all you're catching up with it. I think I've got it the right way around. So you could have quite a variation in the possible temperature that you see from our vantage point.
So I suppose would that translate then to different density contrasts that you might expect?
Could be something like that, yes.
Perhaps.
Yes.
Okay, interesting.
That's sort of part of the thing which I wouldn't know much about. You know much more about. But that's the kind of thing. Yes, yes, indeed.
Do you have an idea of what you think it might take to convince the wider audience?
I've never been able to convince I'm not very good at that, you see. I'm not sure I'm a good person to ask advice on that question, because I thought the Hawking points thing were pretty convincing. 99.98% confidence, and then people do the analysis a different way. They say, "Oh no, we only get 97.6%." Well, if you do it that stupid way, well, what do you expect? But I don't feel quite like that. There are some issues about this, which do need to be looked at a little bit more carefully, you see. The actual size of the spots, for instance. This is not, you see, we thought that there is a good piece of evidence there already in the Hawking points. We call them Hawking points. People say, oh, no, you're calling them Hawking points because of Hawking's fame and you want to... No, it's really genuinely supposed to be the Hawking effect, the evaporation. What you expect for black holes to do in the very, very, very remote future is that they will evaporate by Hawking evaporation. Of course, if they don't, it doesn't make that much difference to the picture because all you're seeing is the energy coming through. But we're calling them Hawking points because that is the expectation from conventional theory. That as the black holes you see the very, very big black holes that we're getting here are very cold. The Hawking temperature is ridiculously small. But the universe expands and expands and expands and expands. And after something like 10 to the 100 years, you're really looking at that sort of timescale, 10 to the 100 years, that black hole will be the warmest thing around. And so then it starts to evaporate away. And then you get the spots that we claim. Now, it may be that they don't, and the Hawking evaporation is wrong, and you don't have that effect. It doesn't make much difference, because it just means the energy comes through in a different form. And all that we see at this stage, there may be other indications of one rather than the other, but at this stage is all we're seeing is the energy coming through in a spot. And the size of that spot, it is actually on one of my slides, I didn't discuss it particularly. Size of that spot comes about from the amount of spread you get from crossover to what you see from loss scattering. So how much in conformal time is that? And how big should the spots be? And I had this email conversation with Alan Guth, which is a rather strange conversation, because I was complaining, and he was complaining about the spots, and he said there could be some other explanation. I didn't see anything that worked, and so on. So, and then he said, but your spots are too big. They ought to be only, see, the spots are, I like to say it in sort of terms as I understand, they're 8 times the diameter of the moon. So he was saying, no, they're only 4 times the diameter. You got it wrong. Why are the spots so big? It's like, no, it's my kind. He must be wrong. So I emailed Christoph Leisner, and I said, surely he's wrong. So, and he goes back and says, yes, he must be wrong. Comes back to me a few days later, says, he's right. Spots are too big by a factor of 2. And there's another little bit of a stage in the universe expansion, which we believe is due to gravitational wave domination. And that comes in before the photon domination. And that gives you a little conformal time, enough time to make the spots twice as big as they apparently should be. I'm giving you information which is not really worked out fully. These are ideas that we've talked about before, and I think they're in the paper that I hope so, otherwise Christoph may be annoyed with me. The paper that we just put on the web.
I just saw that come out today, so I'll take a proper look of that paper.
Yes. The paper is, I think I agree with everything it said, its overall picture. I think we have a lot of work to do in streamlining the physics and the arguments. And I think there's a much cleaner way of getting the results. I don't disagree with the results that we're claiming.
Yes, yeah. Oh, that should be exciting to.
With a factor of 2, we need. So it's quite a curious story, that. Very exciting with your things, you see, because they really seem to fit in with it. As far as we can see, they needs to be looked at much more carefully, which I'm sure we will. And it also,
go on.
I was going to say that our expectation is that there should be lots more. Is that possible?
So this is what I was going to say. I've begun to look through the whole catalogue. My primary focus was and still is to investigate this potential giant ring. So how the giant arc might extend into a giant
that would be
ring.
really exciting. Yes.
I think one of the things that, well, 2 of the things maybe that need to be considered is one, fundamentally how complicated the data is. But we do have really precise redshifts. So this is quite a good thing. But fundamentally, the data is complicated because of the nature that we observe it in, which is relying on these background quasars. So, without them, you can't see this intervening matter.
I see. Yes.
So you never really.
What quasars you're looking at in this picture?
Yeah. So you look at the quasar spectra that then tell us about the intervening matter. So we don't have this. It's almost like you're trying to map what's in a dark, empty hall by having a bunch of spotlights on the back wall. You can't fully see everything that's in that dark, empty hall. You can only see where the spotlights are illuminating. So that's the nature of one of the main complications with the nature of the data. But another thing is the giant ring, presumably, with it being such a large structure, I'm thinking that the density contrast would probably be smaller than, for example, the big ring, which was really obvious. The big ring, when you looked at it in the Mg2 maps, the magnesium-2 maps, it stood out by eye. It was really visually obvious.
I see.
Yeah, whereas I think the giant ring might require a little bit broader redshift depths, and I'm wondering if there's maybe some three-dimensional aspect to it, where like the big ring, for example, had like a coil nature to it. So it had this, it looked like the front end of the big ring was how do I say this? The right side of the big ring was closer to us, and then the central part of the big ring was contained within a smaller redshift interval, if that makes sense. So it gave this kind of coil. So yeah, anyways, all that's to say is I'm investigating this giant ring possibility. However, I also wanted to start looking through the entire magnesium-2 catalogue, which I have began some really preliminary work on that. I've not got a chance to really investigate what the code has spat out so far. I ran a really simple test just to identify some potential candidate structures. I had a quick look through because I haven't had time to focus on that just yet. And a quick look through, and I think you do find maybe there's evidence of more arc or more ring type structures, which is kind of exciting, but I wouldn't want to go ahead and say, yeah, I found some more rings.
Okay, yeah.
Not yet. So I need some time to
investigate. Thing to me is it's not no. I mean, you're saying there could easily be other instances of this feature.
I think so. It's not been, because we've only looked at that small bit of sky,
yes.
And in that small bit of redshift, there's the potential to find more of these. And so I do wonder, how many
redshift, isn't it? Because I was saying the pass cone depends where you hit it. So it's like spheres meeting. Our pass cone is a sphere in the scattering surface, and the ring explosion is another sphere. And there are different ways those spheres can intersect. They can be different sizes. So there's two parameters here. There's one parameter, which is the size of the ring, which is how early it happened in the previous eon, if you like. And the other one is what is the contact? You see, is it close? Or you see in my pictures, I hope my hands are visible to you.
Yes.
Are they?
Yes, yeah.
Are they? Imagine them as spheres, and the spheres could be almost touching, or they could be almost touching at the back. And this gives you quite a broad range of different temperatures. I think that's right, isn't it? Because you're looking at them, if it's almost touching this way, they're coming straight at you, so that's hotter. If they're almost the backside, they're pretty cold. And maybe the red shift or the blue shift or whichever it is I'm not sure. I'm talking off the top of my head a bit here, but it should be a blue shift when it's coming towards us. That's right. And a red shift if it's going away from us.
Well, I think in terms of, because I think in terms of large scale structure. So you have to forgive me for not being able to see the same geometry that I know that you can see. But thinking in terms of the large scale structure, I think when I'm talking about redshift, I'm talking about the distance and the how far away, how far past, would
to do with, just think, yes. I'm confusing myself now for the moment. Yes. Because a pass cone hits this surface somewhere. Yes, you see, when I'm talking about redshift or not, I'm thinking about the signal from the explosion. It's not the way people normally think about it because they don't think of such events, I guess, in a normal way.
Yeah.
So I'd have to translate that into a different language, which I'm not sure I can do off the top of my head here. That's right. So I'm really thinking in terms of these explosions, because that's what we were looking about before. And we certainly thought about that, but we hadn't thought about that's what we hadn't thought about. That's right, is triggering galaxy formation.
Yes.
We hadn't looked at that at all. That was something completely new. So it's a new feature. All we thought about is direct effect on the microwave background radiation, you see. And that might be kicking it a little bit towards us or kicking it a little bit away from us.
Yeah.
So the microwave background might be slightly heated or slightly cooled.
Okay.
And that was the effects that, see, Vahe Gerzajan and the Polish group headed by Christoph Meisner. Christoph, you see, they looked at these things before. I remember them complaining to me that they couldn't get their paper published. Nobody would accept it.
Oh, really?
And I'd said, yes, we've been having a lot of trouble getting our paper accepted too. But the last thing we'd had a paper. This was me with Vahe Gerzajan, you see. He hadn't really done the statistical analysis in the way people like. He'd had his own way of looking at it, which was some different way. And they complained about that, maybe rightly, and said, well, look, we sent it into the Royal Society. Sent it to various places, into the Royal Society, and we get all sorts of rejections. And then we tried to do what they did. Well, they complained about something and said, yes, we'll do that. Complained about something, yes, we'll do that. And finally, they complained about something and said, surely they're complaining about what we did as a result of a previous complaint. And then they got back to me and said, very briefly, they said, okay, well, we'll accept your paper on condition that your colleague gives a detailed account of how he did the analysis. However, in the meantime, we'd sent the paper to a different journal. And that had already been accepted by the other journal. But you see that Christoph and his crowd were complaining to me that they'd never got that paper accepted. They tried all sorts of ways. So I said, why don't you try the Royal Society? You might get a different response this time, which they did. And they did get a different response and the paper was accepted.
Right.
And then they had two papers, the two different satellites. I guess one was the WMAP satellite and the other was the Planck satellite. And they found these spots. These were the rings. There were two different effects, you see. They were looking for rings. I'm getting myself confused. No, those were the Hawking points. That's right. That's right. They saw these spots. And in the WMAP, they had a lot of spots. And in the Planck one, there were a lot of spots. And most of them were all over the place. But I say, look, if you look at the top 6 spots in both, you find this in exactly the same places, in both WMAP and Planck. Oh, wow. So that's a good chance those are genuine. I don't trust the other ones, they're probably flukes. But those 6 points are probably genuine points.
I think there were also, if I'm remembering correctly, I read papers related to CCC and rings in the CMB sky, or at least I've seen a paper on detecting rings in the CMB. So I do think that's also there somewhere.
There were some papers complaining not to see them, and you look at what the paper says, and you actually see they do see them, which is quite good. There's a paper, I never checked out, but they have Spanish-sounding names like yours, I suppose, and either they're from, I assume, from either South America or from Spain. I wasn't sure which. And it looked like quite a good paper, actually, they'd written. But they did look at our claim, and they said they didn't see evidence of it. Then you look at the data, well, yes, they did. They did see evidence of it. The effect right there in the paper.
Oh dear. So they're definitely going to take a lot of convincing then.
I didn't try. I don't know. Yes. I should have tried.
Yeah. So I think it's a really exciting And it'll be a lot of work, I
Yeah,
presume, to figure out how then that could relate to large scale structure and
yes.
um,
I think there's a
pushing.
lot to do.
Yeah.
A lot to do. But your trouble is, you see, I always got stuck because people have this awful, I'm calling it, I shouldn't call it awful, this claim of the inflationary phase at the beginning, which is put in for a wrong reason. And it doesn't explain the uniformity of the universe. They try to say it does, but it doesn't. I mean, for an obvious reason. You just think of what black holes look like and what do generic singularities look like. They're a mess. I mean, Misner and I think the Lifshitz, Kalatnikov, and Belinsky, the original paper they wrote had a mistake in it.
Yeah.
They claimed that you didn't get singularities in the general case. And that was at the time I wrote my paper, which says you do get singularities in the general case. And then they had to change their mind, and they say, whoops, there's a mistake. Belinsky found a mistake, I believe. And then they agreed with me, essentially, that you do get singularities in the general. You do get wild behavior in the Weyl curvature. Nothing whatsoever like what the Big Bang is like. And this is, people don't address that question. I mean, you've got to have some other explanation other than inflation. Inflation doesn't do a thing. I mean, it's got to be already smooth and some awfully smooth way before inflation gets going.
Yeah.
May I ask one question here?
Yes.
Essentially, how do you account for matter creation? Secondly, the Hawking process depends on matter and the matter creation in the strong gravitational field. And,
you see, the Hawking process is the phraseology we use. They're Hawking points. It's not essential for CCC that the Hawking process is correct. There might be some technical reason why it's not correct. I believe it because of general arguments. I mean, the entropy of black holes, the way that the thermodynamics works, implies that there ought to be an entropy for black holes. And they do, after all, represent a final stage of locally of what happens. So I think it's highly plausible that the black holes do evaporate according to Hawking, but it's not necessary for the picture I present. It makes almost no difference. You see, you could have little black holes. I mean, they're little. They look little, they're huge, but they still are points in the picture of crossover. As far as the overall structure of the universe is concerned, if the black holes do not evaporate and they just remain as black holes, they are still points on the crossover surface. Makes almost no difference to the picture.
Just a slight change of topic here. I've just noticed there's quite a few questions in the Q&A.
Yes, we should get.
Would you like me to go through some of these?
I guess if you finished your, did you have some further questions, or have you finished your questions?
I think, you know, I would say I generally finished most of my questions, which is relating to, you know, well, I did wonder if you had an idea of how many rings you might think would then make the relationship.
One might make an estimate of that. Yes, that's a good question.
Yeah. I think it would be interesting to get an idea of that, and then an idea of what kind of structures we're expecting, size, how many, concentration, these kind of things. So it would be really good to work on this.
One point I was going to, as partly a question to you, in the ring looks pretty good without having a sort of randomness on top, whereas the arc is much more as though the galaxies are not quite so localized on the arc. Is that right? It looks a little more spread out.
Oh, yeah. So you mean in the thickness, I suppose.
Yes, the thickness of the ring or the arc.
Yeah. So, sorry, there's a helicopter going by. It's a little bit noisy.
Your picture, there's a bit more of a scatter in the galaxies, as though they're not quite so localized on the ring shape.
Well, this might be the case, which is why I'm wondering about the specification of how precisely ring shaped the structures would be. So in the data is already quite messy and patchy because of the background quasars. So you see a stronger concentration, but they are along the giant arc. You have a different spread. They're a little bit wider away from
Okay,
the
that's the sort of thing I mean.
line.
Yes, it's why then.
Yeah. So
I mean, there is a sort of explanation that I could make for that on my picture, you see, because in the conformal picture, you have a crossover surface and crossover surface. Now, from down below, you see I'm claiming that your big arc, or great arc, whichever it is, happened earlier in the eon, and the one a lot later, you see, they have to think of the time scale is huge. It's very much compressed. So it's much, much later in the ring. Now that would mean there's much less conformal time for it to jiggle around, you see. If you have a
I see.
cone, that cone might well be disturbed by irregularities, and just local curvature irregularities will scatter it a bit, and so it would not be such a clean ring. But if it's later, in other words, a smaller ring, in other words, that's not quite fair. In other words, it's not the right term to use, but along with it, I mean, it could be smaller for more than one reason. This angle of how you intersect the spheres. So it's not quite as simple as I'm saying.
Yeah.
But you would expect it to be later in the eon, the previous eon, and that means it's not got much of a chance to get scattered by random things. You see, it's a cleaner cone.
Yeah. I mean, yeah, as you say, it's probably not. I know you've simplified it so that I can understand that, but that in itself, that simple explanation makes a little bit more sense as to, you know, if we were looking at something with a greater radius, these larger rings, you know, would we expect them to be a little bit more scattered?
A bit more scattered. Yes, that's right.
You know, yeah, okay. Oh, that's quite interesting. So yeah, no, I think it will be really interesting to maybe pin down some of these, you know, specific points, you know, how many might we see, or how many to convince the wider audience, or, you know, the sizes.
It's fascinating because it's a new, you see, everything we were looking at before, well, the Hawking points was a different thing altogether, but the disturbance in the microwave background, I mean, it's pretty vague. You see, you're thinking, how much does a gravitational wave disturb the temperature in the microwave background? Well, it's pretty vague.
Yeah.
Whereas your thing is a much firmer, I mean, you're actually seeing how the matter is disturbed, and not just the radiation itself, is how the matter directly affected by it, which is something quite new, which we haven't got a handle on before.
Yeah. Yeah, I did do a deep dive at one point into your conformal cyclic cosmology and reading or attempting to read some of these complicated papers. I was searching for whether or not there was some explanation that joined in with actual large scale structure and things like this. So it would be really exciting to.
Let me ask you a question here. Had you known about my scheme before you're searching for the rings, or did you search for the rings completely independently of that? Was that something that had any stimulation?
I think it was the giant arc discovery, the big ring discovery, and then, oh, what about conformal cyclic cosmology? I think it was actually my supervisor that might have pointed at, Sir Roger Penrose has conformal cyclic cosmology. Should we look into that? So
That's
I thought,
interesting. So it was that way around, yes.
yeah, I think so. From memory, I think so.
In a way that strengthens the case, I suppose, because you actually see these rings without. Yes,
Yeah.
it does.
Well, I certainly wasn't looking for rings.
Okay.
Because,
yes.
yeah, the giant arc was. Yeah, the giant arc was.
Answers my question. Yes, thank you.
Yeah, no worries. But yeah, I don't know whether I think that's all my questions. So if you want to answer some of the ones online, I can read those out to you. Let me see. I'm just gonna have to quickly read.
Okay, go ahead. Yes.
So I think the question here is possibly similar to what we were discussing about redshifts, about distance. The question was, from the conformal cyclic cosmology point of view, how old are the big rings expected to be?
It's not a straightforward question, you see, because the size of the rings depends. I mean, there's the size of the sphere, which has to do with how old they are. You see, the ones that are, and when I say in the last scattering threefold, we have a sphere, and that sphere could be bigger or smaller, and that is a direct measure of how old in the previous eon the impulse was. So the gravitational collision of the black holes, whatever it was. So that is a direct measure. But what we see is more complicated related to that, because it depends on how our sphere of past light cone intersects the sphere, and that sphere might be bigger or smaller, but how big is the ring we see depends on how close we see it. So it's a little bit complicated story. It could be as small as you like, and you can only just touch it, you see.
Mm-hmm.
It could be as small as you like, except you very, very rarely see that. Or it could be on the far side, which is probably a bit too redshifted. You wouldn't see it at all, I expect. Is that right? I don't know. I can't comment on that.
Mm-hmm. I'm just having a quick read through some more of these. Any indications? I'm going to ask this question, but I'm not really sure I fully get it. So, is there any indication of the simultaneous existence of multiverses through black hole gateways? I'm not sure on that one, so I just fully leave that to you.
It's a reasonable question to ask, because I've gone outlandishly and say that there is a sort of linear continuation. Our universe is only one of this continuing line, if you like, of universes. When people talk about multiverses, they tend to think of them sideways in the picture, basically. Here's mention that the picture I was showing of this sort of things going like this up. There's another lot going up here, and another lot going up there. That's another picture altogether, which I don't have any reason to believe in, and I don't see quite what they do. And it's opening the what does one say? The box of what's it? The box of demons. Yes. I don't know. I mean, there's no reason to believe in a multiverse. I mean, there is a question related to that, where people tend to talk about multiverses when they think perhaps the constants of nature might be different in a different multiverse. But we have certain collection of constants of nature which happen to be certain values. That's a different question, and I could present a biased viewpoint, but I can't answer it. My biased viewpoint is I like to think that all these numbers are numbers of mathematics, which are hard to dig out, that they're actual mathematical numbers. That might easily be wrong, and then you are more of a multiverse track. So I'm not a fan of multiverse. I'm saying if we're thinking of a multiverse needed to get the constants of nature just right, and people often argue, say, if they weren't just right, life wouldn't exist and so on. I don't think we know enough about what makes life exist. We don't know enough about what makes those constants what they are. That's a major challenge for future science. And I don't think one can answer one way or the other at the moment on that. You can hold your beliefs. Probably hold on to your beliefs as you like, and I'm doing the sort of thing like myself. So I'm trying to say, I think my instinct or belief or something is that these numbers of nature, fine structure constant is the one that people can tend to talk about, but all these things, particle masses and so on, do they come from certain numbers which are there already in mathematics? And I like to believe that. Let's just put it like that. I like to believe. I have no real reason to know. So that was a long complicated answer to
that. No, I'm sure it was.
a long, complicated non-answer to the question, I should say.
Would you like to answer some more from
the
Q&A? Okay, let's have a look. So this is 2 points. I think the first one is a point and the second one is a clarification. So let me just read it out to you.
Okay.
First, the birth and death of the universe in a serial fashion was hypothesized in ancient Indian philosophy. The second point, regarding the point of singularity, there can be time only when there is space. So there was no space-time at the point of singularity because there was no mass. It was just a concentration of energy. Is this a plausible reading?
Well, let's try the second question first. See, I don't think that's correct, you see, in my view. When you say there's no mass, it just doesn't give you any scale. That was the point I was making with the cone, you see. The cone is there, which tells you if you squash down space, you squash down time. Keeps the cone the same cone, but you haven't got a scale. And I need that to get through from one eon to the other. I have to say there is a phase of the universe where the scale, and that scale's time as well as mass at the same, so scale and distance at the same rate. I mean, whether you call the speed of light 1, I tend to call it 1, you see, because I'd like my formulae to, it's just the way you scale it. You see, if I like seconds for time, then I would have light seconds for space, which is not very good because it's teensy-weensy. But never mind. I'm a theoretician, so I don't pay too much attention to the facts going around. But the space and time scale together. So I say the light cone is there, even when you've scaled them away. See, at crossover, you have no scale of time and no scale of space. That's true. But you still have the light cones because one to the other is still there. And that's an essential feature of the picture I'm presenting, is that the conformal, in other words,
I have one question here.
Yes?
Why don't you commit yourself to a completely open universe? And why do you need to
that's
bring
another
it all
question.
Together?
No. That's a misleading picture of mine. I tried to say it, but maybe too quickly. That I draw the universe closed up only because it's easier to draw, not because I believe it. And you see, I did also have this picture where it sort of wiggles around and it doesn't close up. If you ask for my biased opinion is that it's hyperbolic. It's not actually closed. It's not even Euclidean it's negative curvature. Very slightly. And the reason for that is a little bit technical. In order to make the scheme work, it has to have a slight negative spatial curvature. Otherwise, there is a resultant positive curvature due to gravitational waves. And they cause an effective mass content which isn't there as actual mass. It's a slightly complicated story, but the conclusion seems to be that we like to have the universe slightly negative spatial curvature, which I think might be the sort of thing you were saying. So it doesn't close up at all. The pictures only look as though they're closed up because you haven't looked carefully enough at the back of the picture.
I have to try to refresh these questions. There are a couple of questions which I think seem to mention consciousness, which I think is something that I'm not sure if you want to.
That's out of subject.
I was thinking it, so I wasn't sure.
I can waffle all day on that subject. No,
yeah. A separate podcast for that.
Yes.
Yeah, so let me just read this one because this one's a long one. Yeah, I think you know, as I say, there's a couple on consciousness, but I think we might be approaching the end of the.
No, I think it's not a good idea to get on to consciousness.
No.
I can waffle about my own views on that if you like, but I don't think
this might be a nice final question to end on, which is a bit more of a, I suppose, a personal or advice type question. An advice given to aspiring mathematics is to do a lot of proofs. What is an analogous advice you would give to an aspiring physicist for developing problem-solving intuition?
Oh, yes. Well, people tend to ask that kind of question. And one of my answers is not a very helpful one. I say, it's very useful to be lucky. And I think of certain events in my life that triggered certain things which I would never have thought of otherwise. And one of the main things, you see, this is just it's not an answer to the question, but let me waffle on it for a little bit. When I was a period in Syracuse, I was beginning to get seriously interested in general relativity. It was before, I'm trying to think, before I really developed my own ideas very far, but there was a meeting in Syracuse with a lot of distinguished physicists thinking about the universe and how gravitational waves behave and how the mass and gravitational waves behave and so on. And I shared an office with Engelbert Schucking, who is a German who had escaped from Germany from before the war, but he was a very remarkable person because he knew everything and everybody. He knew everything in the sense of almost any topic of interest. He would know if he didn't know the answers, he would know where to look it up. And he used to know the German physicists very closely. He was a good friend of them before he left Germany. And so that's why I say knowing everybody as well as knowing everything. But the other thing was he was also a rather original person. He had new ideas as well, which is a very unusual combination. They weren't always sensible, but they were really original. And he was very useful to me because he taught me two things. One was that Maxwell's equations were conformally invariant. I didn't know that. As you see from what I've been saying today, the conformal invariance of light of Maxwell's equations is absolutely crucial to the whole subject. It hasn't featured very strongly in what I'm saying, but certainly that you get information across and so on. And the Maxwell equations are very much a role for studying conformal invariance. And that was one thing. And the other thing was the importance in quantum field theory of splitting field amplitudes into their positive and negative frequency parts. And I began to think, that's not very conformally invariant, is it? Because what you do is you go and look and see all the modes, and you look at the modes, you do your Fourier decomposition, and you split them into positive and negative frequencies. You've got to do your Fourier decomposition. That's not conformally invariant. So if I'm trying to think of conformal picture, that isn't a very good way of doing it, because the Fourier decomposition is a mess. However, the splitting into positive and negative frequency is conformally invariant. How do you see that? Well, you might think of a conformal sphere. That's the complex numbers compactified into a sphere, and your numbers are on the equator, say, and those which extend into one hemisphere give you positive frequency, and those which extend into the other hemisphere give you negative frequency. And I thought that's a very beautiful picture. I want to extend that into full space-time, and that was the origin of twistor theory. It took me several years to find that idea, but the germ of it was there already. So what I say is it's useful to be lucky. I was lucky enough to share the office with everyone, which set me on this line of thinking, which I probably never have done otherwise. Not much help, because you can't all be lucky. On the other hand, maybe I would say as a general, I usually say there's not much use really. I would say it's useful. You have to concentrate on some topic which you really understand deeply, but also you have to have a uniform spread. So I like to think of it as sort of a bit like a black hole, sort of funnel like this. But you go deeply into this funnel. Yes, you have to study very deeply into a particular area which you work on, but you've also got to keep an eye out of how this relates to other things in a global picture. So try to be global and local at the same time is sort of my advice there. And I think that's probably a good general piece of advice. Yeah, no,
one further.
Oh, sorry. Go on.
One clarification. So would you say that in each aeon, the standard model was okay with the addition of lambda, CDMO, or whatever is right? So are you saying that it confirms that in the standard theory, the Higgs field actually gives mass to the particles? So in each aeon, do you have the usual soup in the beginning, and then you have the recombinant epoch, the light escapes. Is that consistent with your view?
I'm not sure I heard the main point of your. I couldn't quite pick it up.
The question within each aeon, do things proceed?
Yes.
As a standard model envisaged.
You're talking about the standard model of particle physics?
Yeah, in each aeon.
Yes. I mean, the mass, you have to get through a phase where mass becomes unimportant. That's the argument. But I mean, you can look at the equations of a massive particle, and it's really the cosmological constant which becomes important rather than the mass. I mean, you can look at how it behaves as you get to crossover. The mass basically has to go away. And I have an argument. I'm not sure it's answering your question, but let me give the answer to some question, which might be connected with yours. That is to say, one thing which makes the case that maybe mass becomes unimportant in the remote future when you're looking at a theory with a positive cosmological constant. You see, what do particle physicists do when there's the first step when they study particle physics? They when I say the first step, maybe it's not the first step, but the very early step, is they look at the two things which are Casimir operators of the Lorentz or the Poincare group. The Poincare group has mass and spin as its two most fundamental things. Those things, mass and spin, are absolutely conserved. That's the idea, you see. Now, you see, I say, well, if you're thinking about cosmological constant, which we do have apparently, something like that, then we have not quite the Poincare group, we have the de Sitter group. And if you look at the de Sitter group, the mass and I think spin may still be a Casimirian, but the mass is not. It has a correction to it. And that means that maybe it makes sense to say that mass fades out in the very remote future. So the picture I have does, in a sense, require that mass is not a fundamental constant, but in the remote future, it fades out. It takes a long time to do it because it depends on when the cosmological constant becomes dominant in some sense. And then your mass becomes irrelevant, and that is essential for being able to get across from one side to the other. And in some sense, if you look at your equations right, that the mass becomes dominated by other things, by lambda, in fact, by the cosmological constant. And you have a way of a conformal scheme which works within itself, where mass becomes absent. Although there is an issue with dark matter, because dark matter has to have a mass. And my view is that the dark matter does have mass, and the particles of dark matter are of gravitational mass. I mean, that's to say they're something like a Planck mass. They're huge. The mass particles would be way off the scale of ordinary particle physics. They would be Planck mass. In other words, I think mass of a flea's eye is the way some people put it. So that's pretty big as a particle physics mass. But the mass of the dark matter is completely unknown, apparently. And to say that it's of that scale, that size, is not inconsistent. As I understand it, I may be out of date, and perhaps it is by now, but I'm told that it's not inconsistent with current observations. That the mass of the dark matter particle, it has to be massive, so it's not a massless particle, but it's essentially gravitation. So the view I would have is it is a form of gravity, but it's a form of gravity which is a particle of a Planck mass. And that is the dark matter. So that has to fit in with the scheme as a whole. And you have to have a conformally invariant overall scheme which involves dark matter as well. I haven't tried to describe that for two reasons. One, it would take too long to describe, and the other is I don't really know how to do it. I just have ideas of how to do it, which are not really completely coherent.
Malaka, would you like to say something about the relation between your giant string and the other massive structures, like Quipu, which have been discovered? And what's the temporal order of these structures?
But the ring size there can't be in our aeon. I mean, it'd have to be pre our aeon, yes. I mean, just from the size of the rings. So
not just rings, there are 5 megastructures. But actually, it is a Quipu.
When I say rings, I'm imagining the arc as a ring. It may not be, of course. I'm taking your word for it. Taking your guess as an act of faith. Yes. No, I think you said it's more than a guess. You said there's some evidence for it to be a ring. Is that correct?
Yeah, there is some evidence that I'm investigating further.
Good. Yes, no, I'd be very keen to know on that one, yes.
I'll keep you updated.
But it would be nice to know how on the sort of scheme I'm putting forward, how common, as you say, how common are they? How big are they on the average? I think that's a good PhD thesis.
Yeah. Yeah, it's a good question. It'd be nice to link the two.
Yeah.
Hmm.
I think we're coming to the end. So
Okay.
maybe quickly summarize what you've been saying so far.
Do you want one of us to summarize or what?
Yeah, just a sentence or two.
Well, I don't know. The talk was a sort of summary as it went. I mean, I think the rings are a fantastic new ingredient in the whole story, which I had never thought of. I'd never thought of looking at how the disturbance in the microwave background might influence condensation into galaxies. I mean, that seems to be what's going on here. It triggers, I mean, I'm ignorant myself of the details of galaxy formation and so on, but I do pick up the argument, essentially, that people don't really know what triggers the initial signal to make a galaxy form. And maybe, so the argument would go, this triggering comes from a really strong gravitational wave disturbance. And when I say strong, it would have to be in the context of what I'm talking about in my talk here, that something like an enormous black hole collision. So in ordinary terms, these black holes are huge. You see, they're galactic clusters, big galactic clusters. And these contain, I don't know how many galaxies, enormous numbers of galaxies, millions, zillions, let me say zillions. I don't know how big a zillion is, but a zillion galaxies. And these, mostly, some matter will probably escape, but I'm guessing that most of it will finally collapse into a few supermassive black holes, huge ones. And those will collide from time to time. And if somebody does an guesstimate on how long that will be, how many times, how big they are, how big the signal could be, how much disturbance will it cause in the early decoupling, dark scattering, whatever it is, to trigger galaxy formation, I would think that's a fantastic new subject, which I had never thought of before. I hadn't thought of looking at that. Wonderful idea. Great. I mean, great to see these effects. And I think it's at the beginning of a story, I would say. A beginning of an important story to investigate these things. You should see more of them, I think. When I say should, let me put it like this. You haven't looked, how much of the sky have you really, of the celestial sphere have you looked at? What factor do you say?
Let's think. I mean, so let's think in terms of degrees. Maybe I want to say maybe around 20 degrees either side. So like large-ish, but then only in a small slice of sky.
So I put my fingers like this. 20 degrees. Anyway, yes. But 20 degrees isn't that much, is it?
No, I'm trying to think of the footprint of the SDS.
Fraction. You're looking at a little spot.
Yeah.
The whole sky. Well, a lot of the sky you can't see because the galaxies in the way and things like that. So probably it's only about half the sky you can see. I don't know, is it?
Well, I mean, I'm using the SDSS data, which is a third of the northern sky. So you're already
I see.
Limited to a third of the northern sky. And then from a third of the northern sky, I've looked at a small patch in that footprint. I think it's in one of those slides that I sent you. It was the SDSS footprint.
Probably in there, yes.
Yeah.
But it does look as though if you spot two of these things in that region, the likelihood is there are lots of them all over the place.
Yeah.
So there's a big area of research. That's all I'm getting at here.
Yes.
It's a big area of research which should reveal a lot of information about the previous eon. I mean, most information that people look for is in our eon. I mean, there's a lot there to learn about.
Yeah.
But this is a direct piece of evidence about.
So finally, let me close this by expressing our appreciation both from the CPFS and the IIC for the fascinating lecture and discussion. Thank you very much.
Good. Well, I hope it's
Yeah.
useful to people. Thank you.
Thank you so much.
Thank you, Alexia, for coming. I think greatly
Thank
appreciate
you for the invitation. It was a pleasure to speak with you about this.
Good.
Thank you very much. So take care and goodbye.
Bye-bye.
I guess we'll be seeing you at some stage, haven't we?
Yeah, sure. Yeah.
Yes, in May.